Okay, I have some Matlab code here that illustrates this idea that we've been talking about of improving the way we model the symbol rate for our communication system. Okay, so the very first part here is just setting up the Matlab plot defaults. So you don't need to worry about that. But what I want to do next is take a look at some sampling and symbol rate combinations so you get a feel for what's happening with this model. All right, so I started with a sampling rate of 1 times 10 to the fifth, and then I have it where I can play around with this parameter. This parameter actually turns out to be the upsample factor. All right, if you look at this formula here, it's just a relationship between fs, f symbol, and m. All right, so but I want to be able to easily play around with that, so I can make that like a 10.5 and run the code, and everything gets updated. Okay, so we're going to play around with different choices of the parameter m. All right, but let's walk through this a little bit. Fs is the overall sampling rate of the system. That's in samples per second. Fsim, it's got moved. Fsim is the symbol rate, and that it would be given in symbols per second. And I wanted to, again, play around with these parameters. All right, so m, I put this in lowercase now because remember our whole goal was to generalize this from what we were doing before. So lowercase m, it can be an integer value, like in this case, it's shown up as 10.5. It's the upsample factor in samples per symbol interval. Now, I have to admit, sometimes I'm careless and say that this is samples per symbol. Well, with some cases that's accurate, because if the symbol is completely contained in one symbol interval, it would be samples per symbol. But we know we're using square root raised cosine pulses. And so the idea of samples per symbol is not quite right. It really should be samples per symbol interval. Okay, so that being straight, we can move on. All right, so what I wanted to point out next is this function called rat. Okay, the rat function in MATLAB is just trying to find a combination of integers that give you the input parameter m. Okay, so if I have m equal 10.5, then 21 over 2, those are both integers. 21 over 2 is equal to 10.5. Okay, but I wanted to point out that you have to be careful with this upsampling and downsampling model approach. And here's an example of why. Okay, so I'm going to uncomment this. What if we said, all right, I want the symbol rate to be a third, basically, of the sampling rate. Okay, so I just innocently put 3033.3, and if I don't have anything to control this, look what happens. Okay, when I put that in, we're looking for this integer ratio, but because we have this rounding that's going on, look at what happens for m and n. Okay, m is a pretty large value, 99,991, and then you downsample by 3,333. This would take a long time to run, okay, when you're actually running through a simulation. So you really want to avoid those kind of situations, and the upsample factor is a little bit off from what you probably really intended, okay? So you can control this by putting a tolerance factor in for this ratio function, or rat function that shows up in MATLAB. So when I rerun this, maybe I had too tight of a tolerance. Okay, when I rerun this with the tolerance factor, I get numbers that are probably more representative of what I really meant in this example. Okay, so m equal 30, n equal 1. All right, so you get the idea. The rat function is just coming up with a ratio of integers that approximates m. You have to be careful with that because sometimes that ratio can give you something that would result in a crazy long simulation time. Okay, so in general, I'm going to put this in here, and if I want a little more accuracy, I can always change that tolerance setting of the rat function. Okay, so let me get rid of this. Okay, rerun this because I'm really interested in playing around with this case where we're looking at 10.5 for the upsample factor. Okay, so when we have 10.5 for the upsample factor, I think it makes some sense. We're going to upsample by 21 and downsample by 2. So when you take that ratio, we get an upsample factor of 10.5. Okay, what I want to do next is take a look at the square root raised cosine pulses. All right, so it turns out that the way the author wrote the M files, or he wrote Matlab code to do SRRC pulses, he ended up scaling that by the upsample factor P. And there's lots of good reasons for doing that. All right, so when you call this function, the call is pulse equals SRRC, then you give it the number of symbols that the pulse extends over, you give it the roll-off factor, and then you give it the upsample factor P. Okay, so he has that in documentation as P. We start letting P equal to M, all right, so that we can look at the different cases that we have involved for the upsample factor. Okay, so I want to point out, we generate the transmitted signal by upsampling by cap M, all right, and cap M is typically bigger than lowercase m, because many times you have to downsample by an n value that's not equal to 1. Okay, but what we want ultimately is this upsample factor of m. All right, so that means the square root raised cosine pulses, if you think about it, they're scaled wrong. Okay, they're too small by a factor of the square root of n. Okay, so, this is kind of in the weeds. If you don't understand that detail, don't worry about it. But sometimes, when I've been playing around with making this code work, sometimes you have questions about, wow, is the scale of this signal exactly right? Because if it's not scaled right, it's certainly not going to downsample into the symbol values that we're expecting. Okay, so this is just a technical detail that is necessary. I wanted to point it out. But when you're sorting through and making a mental model about how this all works, this is a finer point that you don't need to worry about. Okay, I have a plot of that, and I wanted to show it to you. If you took a specific example, all right, we make pulse shapes with an upsample factor of cap m is 21. Okay, and then we make another pulse with an upsample factor of 10.5. You should know, because they're sampled at different rates, they're going to be different lengths. So if you plot these in Matlab, you get this, right? It looks a lot like flattening the curve. Sorry, maybe it's too soon for coronavirus jokes, but here we go. We have this this is not the initial pulse. This is the downsampled pulse, and we had to scale it by square root of 2. So that we would get the proper size, so that when we do the C filtering, we get back symbol values. All right, so that's the point I wanted to make. Okay, next, I wanted to generate an eye diagram. Okay, and it occurs to me, sometimes I use eye diagrams in 2 different contexts. So I'm not really consistent with that. So many times I generate plots that would be more accurately described as soft decision diagrams, but I actually call them an eye diagram. Okay, and so I think the reasoning of that is pretty typical. These terms get conflated together because when you see an eye diagram, it tells you when to downsample, and if you then downsample at those times, when the eye is open, you get the symbol values. So when you look at a soft decision diagram, you can kind of infer when the eye diagram opens. And so people tend to call the soft decision diagrams the eye diagram even though it's really, you know, a soft decision diagram. Okay, so let's take a look at the code. I generated some symbol sequences, and then I had this really clever one-line code to generate the upsampled signal from the YPAM symbol values. Okay, so there's an upsample command in Matlab that lets you insert zeros in the right way, like we've done in the past. Okay, so this is just a shortcut version of what we've done before. All right, here's the scale factor. It's for n that I talked about. And this step is downsampling. I put it all in one line. I'm starting to get good at MATLAB, right? So there you go, take a look at that. Next, we do receive filtering. You know, notice I didn't flip it. I didn't do the flip left right to do the receive filtering because square root raised cosine pulses are symmetric to a flip. So we don't really need to do that step. All right, from here, I've generated an eye diagram, okay? And what I want to do is zoom in here and show you. All right, so if I zoom in, I can look at, you know, this particular point in time, and we move the axis up where you can see it. I'm trying. Oh, this is stuck. Unstick that. Escape. All right, I just want to go down any further, so let me move the whole screen up. Sorry for this technical detail, technical problems. All right, so you can't see that very easily, but this is showing up at 11.5. Remember, MATLAB indices start at 1, so there's a delay of, or an extra value of 1 here. So we see the optimal downsampling time is, in fact, between sample values. That was the whole point of doing this new method of modeling the way we generate symbols. Okay, so let me conclude with that, and then we'll make another video where we talk about what happens if there's a mismatch between the transmitted symbol rate and what we're expecting as the nominal symbol rate. Okay, so that's where we're heading.